and something we studied in the week 1. Now in week 2, we broadly see the how to deal with the system of linear equation. We'll see the when the system we have in week 1 already know the some system of linear equation have unique solution, no solution, and infinitely solution. So how we'll deal with that? How we'll solve those to get that? When we'll fix, how we'll fix that this system of linear equation has no solution in its solution? Or yeah, Aryan, please you do your turn. I'm not starting till now. You can do your
Yes.
restart.
Hi,
Yeah,
sir. Good evening.
yeah. Hello,
Will
Siddharth.
you will you take doubts in this class, sir?
So by two ways I will go. I will first it's totally depend you or you people that I need to take first your doubt or will start the some conceptual thing. Then in the last I can take up.
So we'll start with conceptual.
Concept, sir.
So
Sir,
start with the
Conceptual.
concept.
conceptual, sir.
Okay.
Sir,
So
Okay, we will asking doubts in later.
yeah.
Sir,
Yes. Yeah.
sir, before you start week two concepts and doubt clearing, sir,
Uh-huh.
I have some doubts in week one. Can you clear them and then you can go to week two, sir?
So what's your doubt?
Sir, it is regarding activity question number 1.5, sir. Sir, the
Okay.
answer,
Hmm.
there are three options which were given right,
Mm-hmm.
and right, but I only take two. I
Okay.
thought the third one was wrong because the wrong because the option says that if A is a real matrix, 3 by 3
Uh-huh.
matrix, then the orders of all possible submatrices of A are 1 by 1, 2 by 2, 3 by 3. I have
Okay.
doubt that 1 by 1, 2 by 2 are submatrices. I agree, but
Mm-hmm.
why is 3 by 3 a submatrix of 3 by 3? It's the same matrix, no, sir.
Yeah, but as you know, right, as you done with the maths one also, so you know, a set is subset of itself. We used to say,
Yes,
so
sir.
you can think it is like that. Like
Okay,
a
yes.
matrix can be a subset of itself.
Okay, sir, and two more doubts.
Hmm.
In graded assignment 6, question
Hmm.
number 6, sir.
Hmm.
Question number 6, just a minute, sir.
So due test is I think is over, no, for the graded for week 1.
So answer will get, sir, solution.
Yeah, I will be uploaded.
Okay.
I think yeah, it's I think over. So you'll get the solution.
Okay.
I think it would be better if you'll see once I will upload today, and so you'll see the solution, then ask the question. It will be
The last question, sir. This is so the first question of graded assignment in which there are infinite many such matrices, sir. That
Mm-hmm.
A B is equal to C. A B matrix is given, C matrix is given, and
Okay.
which of the following options are true for matrix A? So why is it that there are infinitely many such matrices? Because there will be only one matrix which is
Which question you are saying?
question number
Sir,
one,
this
sir.
is assignment one. Question number one.
One, sir. Graded assignments.
This is graded assignment week 1.
Yes, sir. Yes, sir.
So this question, this is the first question. Okay. There are only finitely many real values
Not
possible
this
for
one, sir.
x and y. Okay.
Not
And
this.
finitely many natural numbers. Yeah. So it's
Yes.
asking is a you know right? It is a a system of linear equation in two variable.
Sir,
So
not
just
this one. Sir,
which one?
the question is different.
Not this one.
Not this one, sir. Two matrices are given, B and C,
Okay.
and there is a condition that
Question sequence is different.
sequence is different, sir. Actually, I'll tell you. Should
You should
This
take down.
I think it's
this.
two matrices are given, sir.
That question is not there, sir.
I think this question is not there. So yeah, actually maybe. So let's see. Please wait that I will upload the solution and there you
Okay.
will get the whole.
Okay. Sir, after solution, okay.
Okay.
Thank you, sir.
So first, start the concept of
Yeah,
week
so
two.
let's start with the week 2. So I hope all of you at least gone through the lecture. Okay. And all there is one solve with us assignment that is very, I will say, important assignment to know that what is, or summarizing the week 2, and some simple question you will see on solve with assignment. This is you can use for as a note, or to revise the concept and also know what all the things are in the week 2. So that's why I just open, because we'll see it how the things, like what are the content in the lecture wise, and we'll go ahead. So as here in the week 1 we are talking about the determinant, and the continuing that in week 3, some broader concept you will see about the determinant. So in the third part, so let me start it. So I hope all of you at least know that what is the determinant of a matrix. So it is nothing but it is a kind of define that if you have 2 cross 2 matrix, let's say A, B, C, and D. So for the determinant of this matrix is,
AD minus BC.
so it is just AD minus BC. Similarly, if it is a 3 cross 3 matrix, okay, if it is a 3 cross 3 matrix, so you will divide this matrix in finding of order 3 we want to find. So you can change this to in with the minor, minor matrix, and that is what we call a minor matrix
Cofactor.
Cofactor.
and cofactors, and that using, like, it is we are kind of finding of take this one and accept these two, you can find this minor. And with the, if you take with the sign, so sign is will be like this is plus, this is minus, and this is
Minus
plus.
plus.
So if you do like this, then find the determinant of this minor. Okay, so this is, and like this. Now the next one is, this is A here. Now this will B will come, and again you will do this. You can find the, you can remove this and this. Either then your minor will be this and this one. So like this, you will expand and will get the determinant of a matrix. But so you can think this finding the determinant, it has some properties. So what are the properties? Let me list out. So the first properties is, suppose if you have a matrix here, okay, I'm making just a 2 cross 2 matrix. It will be a deal with the n cross s matrix. Okay, the same property will hold for n cross n matrix. So the properties is, if you add a row to another row, then it will not affect the determinant. So that it means that, let's say a plus c is there, you are adding the second row in the first, and in the first row, and this is b plus t, and this is the same as, so it is saying to be the row operation of first kind. It is called mute yourself. Yeah, hello. Somebody has raised hand. Yes. Okay. Yes, Pawan.
So, sir,
Yes.
can we ask doubts here?
Yes, sure.
Okay.
So this is, I think, say, I used to say the elementary operation of first kind. No, I think, is it correct? It is, doesn't matter which one is elementary first kind, second kind, or third kind. Uh, uh, but yeah, this is one operation. I'm thinking that this is the first elementary row operation, and it's then if you find the determinant of this matrix, it is the same as determinant of this matrix. And the second elementary row operation is determinant of
Column operation.
okay. And please, everyone, try to join with your mail ID. Otherwise, such the kind of message I will get that please admit, or some admit message will always pop out for me. So if it is be good if you join with your mail ID. It doesn't ask such thing. Okay, so if you have this matrix and uh, another operation is, suppose this is the matrix and you are adding, and you are this operation you are doing is like a plus, let's say I am taking a real number, t time, you are adding this row, the second row in the first row with the some real number, multiplying the real number, okay, and adding that. So it is t times c, and this is another one is b plus t times d, and this is as the same. So determinant of this matrix is, what will be the determinant of this matrix? T time determinant of the same, right? T time determinant of the same matrix. And the third is uh, I think, what is the third one? Let me open it. Just multiplying the t
Row,
with that.
row,
Swap of row and column.
swapping of rows or column.
Rows or
Swapping of rows or column.
oh, swapping of rows. Yes. Yeah. Third one is I think, yeah. The second one is yes. Okay. So the third one is, if you swap the second row, first row, as mean to say, if it is A, B, C, D, and if you swap with the determinant of this one, if you have swapped the first row with the second, that means if it is here, then both have the same determinant. Both matrix have the same determinant. So just
No, second is the side.
oh,
Please.
please everyone mute yourself.
Sir,
Yes.
hello.
Yes. Hi.
Sir, you told that you multiple of rows. If
Mm-hmm.
we add the multiple of rows to the another row, so the
Mm-hmm.
determinant is not affected. But you are
Okay.
telling that
Okay. Just let me just a minute. So here, if you see that, okay, maybe I am missing something. That's why it's happening. So if you are multiplying a real number with another row and adding the same, it doesn't. Okay, it will not change. Okay, interchanging of the row. Okay, interchanging two rows of row matrix is change the sign. Okay, and the third row, determinant of new matrix obtained by multiplying in a row C with the row square C times. Okay, I missed that. Okay, so the thing is, it will the determinant of this matrix is the same of
second
determinant
one.
of this matrix.
Yes.
Yes, and here the sign will change. So maybe whatever you are getting the determinant of this matrix, then the determinant when you take it will be the sign will be change of this matrix. Okay, I just missed that. And the third one is the same is here as here. The third one is actually interchanging is done, multiplying and adding is, and just multiplying. So first thing is just, I think, interchanging the row. The first type is interchanging the row. So when you are interchanging the row, this is the here. If you see that, this is the key point to have. The first type, you interchange the two rows, then sign of the determinant will change only. The numeric will be the same, but only the sign will change. And the second type is if you multiply a real number, a row, as if you this is the first type, okay, this is the first type and this is the second type, and in this case if you are doing such, the determinant will be the same, okay. And the third one is what is the third one? And third one is a t time, doing the t time. Okay, third one I didn't mention here.
Scalar.
So
Multiplying by
determinant
scalar.
of A, B, C, D is the same t time determinant of. If you are okay,
T time D.
if you are doing this, if it is a t time this, then it will be the t time determinant of A, B, C, D. This is the name. Okay. So there, these three types are these are called the elementary row operation. So in the third lecture is exactly what we studied.
Hello, I have one doubt here.
Yes, Pawan.
Yeah, the T multiplication should be in C and D also, right? This is common for not only for A and B.
No, only one row.
Only one row.
If you are multiplying t with only one row, then determinant will be the t time determinant of the exact without multiplying the.
Okay, if I multiply with C, it will be T square, is it?
Yeah, if you are multiplying the second row also, then it will be t square.
Okay. Yeah.
Sir, but in week 1, it is
Sir,
given
is
as when t comes out of determinant, then is t is to the power n.
Yes. So that's the meaning here. If you are see that if it is a square matrix, okay, and you are multiplying, see if you have a matrix of order n cross n, okay, and let's say this you are multiplying this t with the matrix, so it will be multiplied to each row, okay. It will be multiplied to each row. This is the property. This is the matrix multiplication with an scalar.
Hello, sir.
Yes.
If you have t into determinant of A, B, C, D, then if you want to take that t inside that determinant, so how would we know that to which row we should multiply t? That
So it will
is
be
first.
multiplied to any row. So it doesn't matter.
It
It
will
may
not
be multiplied
affect.
to any. Yeah, it will not affect. So it doesn't matter. It will be any row.
Okay, sir.
So scalar matrix with scalar multiplication with a matrix is, I mean to say, if you have to multiply each row with the t, and now if you find the determinant of this matrix, so it will be t to the power n. Each time you will t make you out, right? So it will be t to the power n determinant of the same matrix. Okay, when you take the determinant here.
And sir, what about column, sir? Can't we multiply a column?
Yes, whatever you are, so these are called elementary row operation. They exactly similar if you are doing with the column operation. Okay, the same operation with the in the column wise if you are doing. And also you can think why it is true. The same effect will happen. Okay, there is no change. Why it is true? Because of determinant of a matrix and determinant of the transpose of matrix is the same, right? Determinant of a matrix and determinant of the transpose. Let me write it here.
Yes, sir.
If you have a matrix and determinant of A transpose is the same. Because of this property, whatever you are doing in the row operation, it will be exactly the same with the doing the in the transpose. That's why if you are doing the row operation, you are doing the here the elementary row operation here, whatever the row operation you are doing, the same operation if you do in the column wise, so it will be the same effect. Means here is, if you see that, what do you mean with that? If you are doing like this, okay, let me erase it here, and if you are doing like this, the same result you will get. This is the exactly correct. And another one is if you are swapping these two. Okay, if you are swapping two columns, so let's say this is here become B and D is here and here is A and C. If you are swapping, then again sign will change because of the same region. Transpose, determinant of transpose and determinant of the matrix is the same. That's why. And the third one is here, whatever you are doing, if you are doing with the column wise, t time here, third one is, sorry, the second one as here is. So let's say it is here. Let me erase it here. Okay. And the thing is, you are doing like this: t time b plus here and t time d. If you are doing, then determinant is exactly the same. If you are doing row operation or column operation, but do accordingly as here is specified. Okay, the same. Okay, where is that? This one. Then it will not. As whatever the row operation you are doing, it will be the same in the column. Okay. And you can see that these are the property of the matrix, like determinant of the matrix. Like see that this is the determinant of the A, and determinant of the A transpose is the same. And another property is determinant of a matrix multiplying two matrix and getting the determinant. Okay, so it will be the exactly determinant of A into determinant of B. And because of that real numbers are commutative, when you are doing the multiplication, it is a commutative. The same thing will happen with this commutative property of multiplying the matrix also. That's why this AB and BA have the same determinant, and which is equal to determinant of A into determinant of B.
Yes, sir.
Okay, so this is I think in week 2 only. Oh, let me open it here. I think so. This is all about in week 2 only, the properties, and let me open it, and how to find the determinant that is called cofactor and minor. So removing this one means if you are taking with respect to this one, that is called, let me open it here. This is called minor. Minor is that suppose you have A, B, C, D, okay, D, E, D, F, G, H, I. Suppose you have a matrix. So minus is with respect to some entry. So minor for this entry is exactly for this entry is this matrix. Okay. So it will be E, F, H. Yes.
F H I.
And minor for
B.
this one is, let's say this one is
B.
for this one is, it is going
D.
to be
D F
D F G
and
H.
F and I. So this is going to be your minor. And cofactor is
changing sign.
you are writing with the sign.
Sign.
Means if your cofactor is you are writing with the sign. That means here for sign is actually this one. This is plus, this is minus, this is plus. Okay. And for this one is again this is minus, this is plus, this is minus.
Sign
And
change
this is
according to
plus, minus, plus. Okay. So this is the thing. If you want to remember it, there is if you don't want to remember it, please everyone mute yourself.
-1.
Yeah, something is formula, no? What is that
Yes, sir.
formula?
-1 raised to the power raised to the
I plus j
Minus 1 raised
position of
I plus J.
I plus J.
position minus
into
into
m of I
m
j.
of
Yeah.
I plus
I
I
plus.
j.
Yes, this is
I
the
know I
formula.
plus not m of I j.
So if you, this is 1 1, so this is called 1 1. Okay, this is called 1 2, and this is 1 3. Because of that, if you see that -1 to the power 1 1, it is going to be square, so that's why it will become plus. If you see the third one, the 1 2 is going to be your
3.
3, that's why it will become minus. So it will apply the whole entries. So this is going to be 2 1, this is 2 2, 2 3, 3 1, 3 2, and 3 3. Because of this one, this is the sign decided, and if you with the minor, if you adding the sign, then it will become cofactor. And now if you want to find a determinant of any order, this suppose this is n cross n. Okay, suppose this is 3 cross 3, but suppose your matrix is of order n cross n, then take a row. Okay, take a row with the sign, means cofactor, taking the cofactor and expand with the entries of the first row or second row, any row. Take the any row, take the cofactor with respect to that and expand the matrix, find the determinant. So this is a process to find the determinant of any order. So I think this is in the this is
Sir,
only in
one doubt.
week.
Sir, sir, one doubt. Sir, you told that
Yes.
which one is
What's
cofactor?
your
Actually the hello.
yes, yes, yes. Am I audible?
Hello, sir.
Yeah, hi. I think
Yeah,
he is. Yes.
Sir, am I audible
Yes,
now?
Prashant, you are now audible.
Sir, I was asking that which can I call minor means that small the determinant of that
Yes.
small matrix or
Huh, the
the
without the sign. The without the sign is called minor, and if you add the sign, it will become cofactor.
no means the matrix or determinant of that matrix.
So that determinant that minus this is called minor matrix. Okay. This is
Yeah.
called
Oh,
minor
if
matrix.
we then we find the determinant of this matrix, then we can call that number a minor, isn't it?
Yes, 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 yes. Once you find the determinant of that matrix, it will become minor. That is called minor. And it is called minor matrix. And if you find the determinant, that is going to be the minor of that matrix.
Right.
Okay.
hello, sir.
Yes, I think.
Then, yeah,
Please, everyone, mute yourself. I think some noise is coming from home. I think this one. Okay. Yes, yes,
yeah.
yes,
Hello,
Bill.
sir.
Yes, yes,
Yeah.
Bill.
Actually, I want to know like minor of 2 cross 2. Like minor of 2 cross 2 is like, yeah, like
Yeah, the same
DFG,
number it will get. Yeah, if it is a B, C, D is there. So minor
CD.
for this one is actually D. Minus for
Okay.
C is
M
actually
of
just D. Okay.
M of 1 2 is like first row, second column C, no?
So you know, right? It is a 1 cross 1 is
Yeah.
also a matrix. No, you can think it is a matrix. Eliminate these two, and this will become a 1 cross 1 matrix. Right?
Hi,
Okay,
sir.
okay.
Hi, sir.
Yeah. Hello.
Sir, I have a doubt 2.1. Which one is solve with us?
Okay. What is out here?
In a first question,
Mm-hmm.
it is given find out M23,
Hmm.
but M23 represents the matrix, a submatrix. But
Okay.
how can we write the answer in like integers? M23 here it is not given determinant of M23.
No, it is asking for minor. No. So minor is actually that number determinant of that matrix. See that if you see hint is also written submatrix relating the row and the third column. Calculate the determinant of submatrix. That is called minor. No.
M23 represents minors or minors matrix.
So
M23 minors
M23
matrix.
represent minor means minor, and that matrix is called, you can say, minor matrix.
Yeah,
Okay.
yeah. So
And that
M23
number,
represents
once you
minor
find the
matrix.
determinant, you can say that is minor.
So here it should be written like a determinant of M23. Find out that.
So that's why the minor word is saying to be exactly the determinant of matrix. Determinant of matrix is called, you can say, minor. Or if it is not clear, so see the key point. What is the key point written here? What do you mean by M23? See that after finding the determinant. What is 1 1 after finding the determinant? So according to the key point, you can go also if it is definition is not clear. And definition means if it is a minor, minor is written means after finding the determinant. Okay. And if you say the minor matrix, that means your matrix is this one, whatever the minor you are, any matrix you are taking. Okay.
Okay, sir. Okay, thank you.
Okay, so this is, I think, in first lecture. Let's move ahead to the second lecture. In the second lecture, what is that? In the second lecture, about the Cramer rule. So now we back to the. This is all about the finding the determinant of a matrix. Now let's back to the Cramer rule. So Cramer rule, when we apply, when you have a system. So let me tell you that Cramer rule you cannot apply for each matrix. Okay. The Cramer rule we
Yes,
will
sir.
apply, sorry, each matrix, sorry, a system of linear equation. So let me tell you the Cramer rule only apply when your system has unique solution. Okay. When your system of linear equation, so what is the system of linear equation? Please everyone mute yourself.
AX
Hello,
is
sir.
equal to B.
How we know like the system has unique solution is like D is not equal to 0.
No, it is not always. So I will tell you. Okay. Please, you can mute yourself. Some noise is coming from Pawan Gupta. From the Pawan Gupta. Okay, someone else is there also. Yes. Okay. So, see, the way you will get a system of linear equation has unique solution or not, that is only will happen. See, when it will, well, so let me tell you the first, what is the system of linear equation. Then I will tell you when it have unique solution or not. Okay.
Okay, sir. Okay.
So system of linear equations is nothing but how many numbers, how many variables are there. Number of, like suppose mean to say, linear means, the word linear means, as you
Degree
know the
1.
function.
Degree
Suppose you
1.
know the function or equation, as you used to solve. Please everyone mute yourself. Okay. So as you know, when you like you done with the polynomial also in the maths one, so right, quadratic is there. Quadratic means what? That polynomial or that function which is a
His power.
polynomial
His power.
degree. Pawan, please mute yourself, or you can go to some other place so that your background noise should not come. So some background noise is coming. So the 9x plus, let's say this is, so as you know, this is an equation, quadratic equation you can say. So this is a equation, but it have degree 2. So if a system, if you have equation which have, let's say this one, so this is an equation, and this is a, you can say, a linear equation. This is a linear equation. So now see, this is in one variable, but the problem is when you are in multivariable. So I hope you seen that in the first lecture, how an equation will become, how a problem you can format that problem in a multivariable, but it will be a linear. Means here each variable have one degree should be one. That's the meaning of linear system. A system, why it is the system word is uses, it should have, means this is one, let me one by one tell you. So this is a linear equation in one variable. Let's say the case is here, x plus y is equal to 2, or let's say, okay, this is a linear equation. It have two variables. See that it have two variable, and each variable have degree 1. So this is a linear equation in two variable. Okay. And now suppose you have a equation, okay, not only one equation. Let's say this is the, you have a problem, and when you converted that problem in equation, it will become, you got two equation. Okay, let's say this is 3, this is, so when you converted that problem, you got two equation in two variable. Such kind of system, you can say, whatever the structure you got, this you can call it as a system, and each equation is a linear. So system of linear and linear equation. So that's why it is, you can say, that's why the naming is system of linear equation. So single this equation, even you can say the single equation, you can say, is a system of linear equation now itself. Or it can more, where more equations are there, you can say still the system of linear equation. So suppose you have a system of linear equation, but here is to be note that number of variables and number of equation should be the same. Then the Cramer rule be applied. There are, you can say, now the condition will come for the Cramer rule. What is the condition? That, let me write, number of variables, okay, and number of equations in a system, okay, in a system
So it has
should
to
be
be a
same.
square matrix, right, sir?
Yeah. Why? Because we need a square matrix. You know, the finding the determinant of matrix is for a square matrix. Okay. So for that, when we apply the Cramer rule, actually the Cramer rule uses this determinant of a matrix. So for that, we need a system which have the same number of equation, and so have whatever the number of variables are there, that those many number of equations should be there also. So this is one condition. So suppose your case is here, x plus y plus z is equal to 2, and let's say 2x plus 3y plus z is equal to 1. So see, in this case you have 3 variable but only 2 equations. So you cannot apply the Cramer rule here. Okay, so you cannot apply here the Cramer rule. Now this is one condition, and let me write the another condition for the Cramer rule.
Sir, simply we can say that when the system has solution, isn't it?
No, still this system has solution. There is no issue. It may have solution. Okay,
No,
so it
may
doesn't
not have
matter.
single solution. No? If
But
we
yeah,
are having 3 variables and 2 equations are there.
equation. So in this case, it doesn't have the unique solution. It have infinitely. It may have
Yeah, unique.
infinitely.
Sir, I missed that unique word.
Yes. Yes. So, and the second condition, now the second condition is whenever, so suppose now, hope you know that in the first week how to convert a system of linear equation in matrix format. That is also a system of linear equation, but in matrix format. So for this one, how you will convert? So this will become 1 1 1, and this will become
1
2
1
3
1
1.
3 1.
Now, and this is
XYZ.
x, y, and z. This is 2.
2 1.
Please, I think, please, yeah, Emma, please mute, because yeah, some background noise is coming from your side when you are unmuting yourself. So see that now this is called coefficient matrix. Okay, this is variable and this is b. That is coefficient. Let's say this is a, and this is variable. In generally, you can say capital X. Okay, variable matrix you can say as a capital X, and this is b. So this system of linear equation now changed in this format. So this is your coefficient matrix, and this is after that. This is b actually. There is no main. This is the main thing. Now here the second condition is applied for this A matrix, coefficient matrix. What is the condition? That this coefficient matrix should be square matrix. Okay. Once you are saying the square matrix, then you will see that this condition itself fall. The number of equation and number of equations and variables should be same. When you are saying the square, this coefficient matrix should be square matrix, then that means this first condition itself will follow. And the second condition, and an extra thing is that this determinant, this coefficient matrix, determinant of the coefficient matrix should not equal to 0. This is the condition. If these two conditions followed, you can say, then you are able to apply the Cramer rule. So now you will see the reason why we needed this one. Why we needed? Why we are, once this will be done, then we are able to do. Why it is needed? Let me tell you the solution. When you are start solving, you will see that why we needed determinant not equal to 0 of the coefficient matrix. So let me form a system of linear equation. Let's say this is the system of linear equation. A11 x plus, okay, maybe I think the two system of linear equation of 2 variable and 2 equation will be enough to deal with that. So let's say this is A11 x plus A12 y is equal to, let's say, a. Okay, and the second thing is, let's say, b, or you can say A21. Now A21x plus A22, okay, y equal to, let's say, this is b. Okay. Now if you change this system of linear equation in matrix format, it will become A11 A12 A21 A22. Okay. Now your variable matrix is here, and this is your P, matrix P. Okay. Now see that this coefficient matrix is a square matrix. This is your variable matrix, and here is the right side of the equation. Now the Cramer rule says this x, exactly this variable, if you while solving, so Cramer is actually used to solve the system of linear equation, no? So what is going to be the solution for x is exactly, so let me write that, that is
D1.
something called
Yeah. X is equal to D1 by
a
D.
something name is there, let me the name is in the notation form is, let's say ax is h, yeah, no, ax, not ax,
D1, sir. Because D1 is
a1, let's say a1.
okay.
Yeah, a1 is going to be now your this matrix. So think about your matrix is this one, the first row replaced by this column, this sorry, this matrix. This is going to be your a b, and this is 1 2, and
Hello,
this is
sir.
2.
Hello, sir. I think
Yes,
the screen are stuck because as you write, I'm not able to see.
Yes, sir.
now I think, is it clear now,
No, it's okay,
visible?
sir.
Yeah, yeah,
Okay.
Yeah,
yeah.
now
It is
yeah.
visible.
So see that now your value of x is going to be, so let's find this a1. Okay, let's another find a2. It is going to be your, change the second row with the same, this one, right side of the equation. So this is going to be,
Second column.
yeah, second column. This is going to be a1 1 a2 1. Now the second column change with this right side of that equation. So this is going to be a, and this is going to be your b. Okay. So this is a1 and a2. Now x is exactly the determinant of a1 upon, this is going to be the determinant of the coefficient matrix. See that this is the coefficient we have. This is our a coefficient.
Yeah,
And
yeah.
y is exactly determinant of this a2 upon determinant of this a. Again, the a is the same, and but only the numerator is going to be different, and that is going to be the determinant of a1 for x, and for y it is going to be a2. Okay. So now see that why the reason we needed determinant is non-zero for coefficient is that it is going to be in denominator, and you know, right, denominator we don't want ever to, denominator should be 0. Numerator can be 0, but denominator should never be 0. That's why
Then,
we
sir,
need.
as you're
Yes.
saying, the Cramer rule will apply if the system is have the unique solution. Then how we know the system has unique solution? By D is not
So
equal
the
to
reason is actually this one itself says once the determinant is non-zero. No, this says the system has unique solution.
okay, as I'm
Why the
saying.
reason is, let me tell you why the reason is also. Okay, you know, right, I think you enough to now say that if you have a system of linear equation, I'm writing in this form. Okay, if you have a system of linear equation, this one, so hope you know that what is the inverse of a matrix, and also able to find that, right? I think is it
Yes, sir.
done?
Yes. Yeah, yeah,
So
yeah.
inverse of a matrix, when the inverse of a matrix exists, when a system of inverse of a matrix exists, when the
Yes, sir.
determinant is not should
Determinant is not
non-zero.
equal to. Yeah.
Yes, the reason is the determinant of a is non-zero, then your matrix is invertible. So suppose in that case, when you apply here, when you multiply both sides with the inverse, okay, let's say I am multiplying, your inverse is minus, I am denoting with the minus a to the power minus 1. Okay, inverse is actually, this is not the power, this is, I am denoting the inverse of a. Okay, and I just multiplied both side with the inverse. This is ax, and this is going to be a inverse b. Now once you multiply inverse with the same matrix, will become identity. So that means here this will become identity. Okay, and this is ix, and this is your inverse. Now identity, when you multiply identity with the variable matrix, it will be exactly give the that x y z, and this is whatever you multiply the inverse with the single column matrix, you will get a column matrix. As you know, you can say suppose this is n cross 1 and this is n cross 1, right? It will be, suppose this is n cross n, so this is going to be n cross 1, and when you multiply, the order will come this one and this one, so that's why it will come n cross 1. The in between n is merged, you can say removed. Outer n, outer m and n, whatever the thing is, multiplying a matrix, let's say this is m cross n and b is, let's say, uh, n cross p. So this one should be same. Okay, then the matrix multiplication will be possible, and the order of the after multiplying it will be the
M cross P.
n cross p. The whatever the matrix will get, the order will be m cross p outer. The
Yeah.
same thing is happening here. Once you multiply the inverse, once you find the inverse, it will be the same order as the matrix A you have, n cross n, and you when you are multiplying this A inverse with D, it is going to be n cross n. That's why it's give you the actually this is another method to solve a system of linear equation. This is another method to solve a system of linear equation. Now I was talking about why it is okay. So why so in this case the system is also see. Yes.
Sir, could you scroll up a little? Scroll up. Yes. How do you decide that in A1 and A2 that the column vector AB will be in which row? I mean, if we took for suppose X term, A1 denotes the
So
removal of X.
let me tell you that you can the reason how you'll decide that. So you can think that let's say your variable is you can right, we can in place of xy you can write also x1 x2 also, right? So let's say I'm suppose I am changing with the if there is a problem, so let's say I'm changing with here x1 and this is your x2, this is x1 and this is your x2, so then your system will become here x1 and this is your x2. Is it fine now? Now what is x1 here? So to get the x1, you can change the first column. Okay, to get the x2 here, this is the, let's say this is x2. To get the x2, change the second column, right, with the right side of it. I think it would be nice to remember. It will
Basically,
make
I
easier to
have
remember.
to put these vector in that column which we are observing. For example, for x1, we have to replace the x1 column and put it A and B.
Yeah,
And for
suppose your
y2, we have
system
to
of
eliminate.
linear equations is n cross n. You want to find the xi variable. You want to find the value of xi variable. So change the ith column with the right side of the equation, right? Ith column.
Okay.
And that is going to be find the determinant with the same formula. So this formula actually will this whatever the formula is there, no, it will work for the n cross n. It will extend only. Only the extension will happen. If it is n cross n in n variable, so only the extension will happen with the changing, right, with the column changing with the right side of the right side of the equation. So this
Sir,
will yes
what is
yes.
extension means?
Extension
will
means
happen.
your means you are changing means your system of linear equation is order of n cross n. That's the meaning here. We have only 2 cross 2, no? So we want to
Yes.
in the order of n cross n. Let's say this here you can see the in the let's say I'm showing you the second key point. So you see that this is your system of linear equation in 3 variable. So 3 variables, so 3
I
equation
understand.
needed. Now see that how it is. Ax1. Okay, so I wrote x1, no? It's better to write Ax1. Sorry, I wrote A1, A2, A3. It's better to write the matrix is actually Ax1. Similarly, Ax2. Similarly, Ax3. So what is Ax1? Change the first column with the right side of the equation. See that what is Ax2? Change the second column. Similarly, what is Ax3? Change the third column. And find the determinant of the data of xi upon determinant of it will be something, it will be extended to any order of a matrix. Yes, I think somebody is want
Sir,
to
can
ask.
you go to the
Yes.
page?
Yes.
Not that where you were writing, sir. I didn't
Okay.
Understood the last part. Can you repeat that?
Which part? Here,
Yes,
this one.
this one, sir. Complete.
This
Complete
one.
this.
This
Last.
one.
Yes, sir.
This one. This person.
No, sir. From starting.
This one. This person.
Yes, sir.
This person. I am saying you have a system.
What were you were telling? I didn't got at all.
I am saying you have a system of linear equation where the coefficient matrix is of order n cross n. Okay, this is where x. So x is actually also order going to be n cross 1 and B is going to be n cross 1, right? Eh,
Yes,
Are
sir.
you getting this one?
Yes, sir. I am getting.
Okay. So in this case, suppose your matrix is invertible. When your matrix is invertible, when the determinant of the coefficient matrix is non-zero, in that case, your matrix is going to be invertible. So suppose
Okay.
A is going to be invertible your matrix. Now, suppose your inverse of A is actually A to the power minus 1. I am denoting it. It is also going to be n cross n, right?
Yes, sir.
Now you are multiplying A inverse both side, right? Both side. This is the multiplication I am doing, both side. And
Yes, sir.
once you multiply, you will get identity with the same matrix.
Uh,
And here is
yes,
going
sir.
to be your n cross n matrix multiplied with the n cross 1. And once you multiply the, right, what will get? A single column matrix. This is the
Yes,
mean
sir.
answer. So this is
Okay, and
also a method.
that will be the solution.
Yes, this is also a method to solve a system of linear equation. Okay,
Okay, sir. But
this is
finding
one.
the inverse is difficult.
Yeah, actually it's take time. That's why. Cramer rules also will be applicable only you can say 3 or order or 4 order of matrix. But now if you are n like 5, 6, 7 order matrices are there, or even I can say, see, this is done with the square matrix only. Your system is kind of a square system, you can say, or your coefficient matrix is square. But what the case when the system is not square, that coefficient matrix is not square matrix? How we will deal with that? In that case, the third, I think, what is that in the third lecture is that Cramer is the first system of linear equation with invertible. Oh, so see that by the third lecture, whatever we discuss is actually the third lecture. This is the exactly the third lecture. So whatever we
Yes,
discuss.
sir.
So solution of a system of linear equation with the invertible coefficient matrix. Exactly what we did here, what we discussed here, exactly the same. So this is, that's why I said this is another method. I thought it is not taught in lecture, but yeah, it is actually in the lecture. So there are two method we done. Cramer is done, and the second is invertible. So inverse, using the after finding the inverse, we done. So see that how it is happening. So in these two cases, it is saying that when the system of linear equation has unique solution, in that case you are able to do. And reason is also the coefficient is going to be 0, determinant of the coefficient matrix is going to be non-zero, then in that case you are able to apply in both, in your invertible case also, or in the Cramer rule also. Now we have, so this is only for the, no, in the both cases the coefficient matrix needed a square matrix. But what the case when the coefficient matrix is not a square matrix? See, there are such problem case, there are, when you are converting some real life problem and you got that the coefficient matrix is not a square matrix. That means number of variable is not same as the number of equation. So how we will deal with that? So that's why there is a bigger picture. And also always I like this, that always that method is always very much useful. And it is actually, whenever you have a system of linear equation, don't try to with the Cramer or this invertible. My suggestion is that always use this Gauss, what is that the name is?
Gauss elimination method.
Gauss
Elimination.
elimination method. That is a very easy and actually applicable, and it doesn't needed much calculation. Only whatever you deal with, right, in the finding the determinant, some elementary row operation we know, type 1, type 2, type 3. Only those operation is enough to deal with such system of linear equation. There, now the picture come, this, before going to the Gauss elimination, we needed some forms. So in the in the fourth and fifth lecture, you will see that some forms is given. That is, first form is echelon form, and the second form is reduced row echelon form. To use this Gauss elimination method, how we'll deal with the how we'll apply the Gauss elimination method is actually once you know that what is a reduced row echelon form of a matrix or what is echelon form of matrix. So let's discuss that. What is the echelon form of matrix? So suppose if you have a matrix, okay, let's say I'm writing a matrix A which is any order. So for general case I am writing M cross N. Okay, it doesn't matter it is a square matrix or not. Okay, it doesn't matter here. And let me show you that the word also. If I will write the word also, it will be more proper. Okay, so okay, I will back to the third lecture. I didn't tell you how. I think I didn't tell you how to find the inverse of a matrix. Okay, we'll let you after discussing the echelon. We'll discuss this. Okay, so I just started the site. Let me go with the echelon form. Then we'll discuss. That's all I think in 2.1 it is there in 2.2. So there, if you see that there is two solve with us. One is 2.1 and another one is 2.2. So now the word is here. The what is the row echelon form and what is reduced row echelon form? So the basic idea is, let me tell you the basic idea. Suppose if you have a matrix, okay, which is M cross M. This you have a matrix. We will do some elementary row operation. Okay? Only the row operation. Now here the term column operation will not talk about. That's why in lecture you will not find actually. And also sir, uh, Sarang sir didn't taught the teach this column operation. Why? Because Gaussian uses only the elementary row operation. Okay, that's why in that lecture, in the first lecture or in the first week, you didn't see the uh, elementary column operation, because Gaussian is only uses elementary row operation, you can say. Now suppose you have a square matrix and you are using the type 1, type 2, type 3, whatever you just now used in the uh, in finding the determinant of a matrix, or the properties, you can say which property you have seen in the first lecture of this week. That property, that is called property type 1. Once you apply the type 1, okay, what is the property you will get for the determinant? When you apply type 2 row operation, what is the property? When you apply type 3 row operation, elementary row operation, that is called, what is the determinant as of a matrix? The same operation whatever are doing there, do the same here. So let me tell you with an example. Okay, that would be, let's say I am writing a matrix. Suppose this is 1 0 minus 1, this is 2, or let's say this is 2 is here. Okay. This is 2 and this is 1 here. Okay. This is 1. This is 1 here, and this is minus 1, and this is, let's say 0 is here, and this, suppose this is 3, and this is minus 3, and this is 3 is here, again 3. Okay, suppose you have a matrix, this one. Okay, so I will do the same operation, as we did in the matrix, in the determinant. What I will do, I will do those operation to change this matrix in some different form. Okay, in different form. So okay, okay, let's continue with this one, then I will tell you. So I am doing what I am doing. I am doing I am taking this first row, and I multiplying the first row with 1 by 2. So the notation is like this: 1 by 2 R1. R1 means row 1. Okay, so once you did this, what you will get the matrix here? This is 1 here, this is 0 here, this is minus 1 by 2. I did only row 1, so rest R will be the same. Okay, am I audible?
Yes, sir.
Okay. So I did this operation on only the row 1, so this means here this. Now I made this one, and what I am doing, so the row operation is sorry, echelon form. Now tell you the why we needed this one, why I am doing this one. So actually I am trying to convert this matrix in row echelon form. So what is row echelon form is, suppose your matrix is here and it is in the form of this one. Suppose this is 1 0 0, or let's say this is something 2 3. Okay, and this is, so this is called pivot element, and pivot element should be 1. Okay, so and below of the pivot element for the particular row, all should be 0, and right side of the this, see that the next, in the next row, this is going to be 0, and right side of that 0 is actually, it should be either 0 or 1. Okay, suppose here is 1, here is 1. Okay, suppose here is 1, then these are could be, now this is called pivot element, except the pivot element other can be either uh, either it can be 1 or any number. Okay, so suppose this is 3 here. Now the next is going to be 0 here, and below of the pivot is also should be 0, and next is, this one is going to be your 1 only. The third row pivot element for the third row is here. So in such form it is actually called, this is called a row echelon form. So suppose the case is this case is also, this is one type. Another case is also possible. Suppose here is 0. Suppose here is 0. Okay, suppose is here 0. So the non-zero entry, see that non-zero entry for the second row is going to be this one, non-zero. See the word non-zero entry for the second row. This is your second row, is going to be this one. So in the row echelon form, non-zero, the first non-zero, this is called the first non-zero entry. The first non-zero entry is called, you can say, the going to be pivot element, and it should be 1. So make it 1. If it is, this is going to be non-zero entry for the second row, it should be 1. So here is, if it is 3 here, then it is not in the row echelon form. Then you have to change in, it should be in, if here is 1. Okay, if here is 1, then the next is, now this is your pivot element for the second row. So in the third row, this should be 0. After in the pivot element, below of that row, that is going to be third row, it should be 0. If it is non-zero, then again it is not in the row echelon form. These are the some cases. So there are different forms. So let me read out the word, then it will be, I will tell you the more about it.
Sir,
How
sir, I have a question.
I have one doubt.
Yes.
Sir, so pivot element, you are telling that one is a pivot element. Pivot element is there in all the rows.
Not need, no, it is not necessary. It could be, see in this, in the third row, there is no pivot element. Third row is actually 0 row.
What is pivot element? Means
pivot element is first leading entry, or leading entry, you can say. Pivot element is the first non-zero entry, you can say the pivot element. First non-zero entry is called pivot element.
So in the video, there was one more term used, that was dependent and independent terms.
Sorry?
So in the video, these, I think pivot element was called as independent. Is it the same?
I will tell you what you mean by the independent. Okay? Yes.
So means like, is it only going to be 1, or it can be anything else than 1?
No,
But it should
for
not
the
be
row
0.
echelon form.
Sir,
Yes.
sir, the pivot element is like the leading element, no? The row
Leading entry, yeah. The first non-zero element, on first non-zero element in that row.
Yeah.
So it can be anything, 2, 3, 4, not necessarily.
Yeah,
1.
so it could be 2, 3, but in a row echelon form, it should be 1. Okay.
Reduce echelon form, it should be 1.
In row echelon form, in reduced row echelon, in both, it should be 1.
Yes, sir.
Okay. In both cases, it should be 1.
Sir?
And what
Because in echelon we make it one.
Sorry, one
No,
by
sir.
one.
I
Yes.
think
Yes.
in Echelon there no need to must be the leading element is one, but reduced Echelon form it must be the leading element is one.
No, in row echelon form also the leading entry should be one.
The difference is zero below and above the pivot.
Only the difference in row echelon form and reduced row echelon form is, suppose here is one, no, here is one, no. So in reduced row echelon form, below of that is zero and above of that also should be zero. So if you see that this in row echelon form, but not in reduced row echelon form. The reason is above of that leading entry or pivot element, you can say, is here is not zero, here is 3. Okay.
Then
Sir,
sir, write one example like the matrix have element 2 1 0 1.
Okay. 2 1 0 1.
And in second row 0 2 1 0.
0 2 1 0. Okay.
And in third row 0 0 1 2.
0 0 1 2.
1 2. This
Okay.
is Echelon form or not?
No. So this is not in echelon form. You have, yeah, this is not as this is your leading entry for the first row. This is your leading entry in the second row. This is your leading entry in the third row. So third row is fine, but in second and first row, see that leading entry is non-zero, but it is it is non-zero, but it is not one. It should be one. Then it is going to be a echelon form.
Sir, is it necessary that every matrix can be reduced to echelon form or
Yes,
reduced row echelon?
yes. Not necessary. Every matrix can be reduced to in row echelon form or reduced row echelon form. Every
No,
matrix.
sometimes what happens is we convert all the entries according to echelon form to one, but there is one element in the suppose in the third row which cannot be transformed into zero. Suppose first column would be 1 0 1. That one won't go away if we use
So
echelon form,
here,
and it will
are
be
you saying
restricted
here?
to.
Are you saying here or here? Where is that? Sorry, can you repeat again, please?
I'm saying, sir, that
Hmm.
suppose in some cases, I don't know exactly the metrics. In some cases, what happens when we reduce using row
Row
operations,
operation. Yes.
then what happens is suppose we get 1 0 0 1 0 1 0 and 1 0 1. So in the
101.
last row, so what happens is this cannot be reduced. I mean, you cannot convert it into zero.
Okay.
Sometimes it happens because if we further operate, it will shift either to above or below. I mean, it will not eliminate.
Huh.
So
So why
will it
we
will,
need it? Actually, whatever you are saying, it is actually in the row echelon form.
it's already in the row echelon form.
Yeah. See, for a matrix, there are many ways. There for you can say, if you have a matrix, the row echelon form of matrix can be different also. But reduced row echelon form is unique for a matrix. For
Okay.
a matrix, reduced row echelon form is unique. But yeah, row echelon form can be different also. We'll see
So
it. So let me show you the wording also. So here is see
So,
that.
so one more doubt, sir.
Yes.
So can you please write down this matrix?
Okay.
Row 1 has 1 0 0.
1 0 0. Okay.
Row 2 is 0 0 1.
0 0 1. Okay.
Row 3 is 0 2 3.
0 2 3.
So
So
this will not be in echelon, row echelon, right?
yeah, it is not in row echelon form. As here
Um,
this one fine. This
yes,
is
sir.
the next row is here. But now the third row here should be
Yes.
0. Here should be 0.
All the three
This is
elements will be should be 0.
that means
So
in the all
it
three
may
in the third row all three elements should
all
be
three
0.
entries
Should be
so
0.
sir,
Okay.
the row echelon form must be a triangular matrix.
Yeah, it
so
could be
that is also my
triangular.
question. Is
Either
it
see that it is a upper triangular. It is
Yeah,
not in triangular. It
yeah,
is
it
not
must
upper
be.
triangular.
So all row echelon form matrix will be a upper triangular matrix.
No, the triangular matrix is when you will say the triangular matrix is generally you will know that for a square matrix you will say word used for triangular, upper triangular, lower triangular. Suppose your matrix is not square matrix, then you cannot use the word.
Yeah, if it is a square matrix, then
Yes.
it must be a upper
Yeah,
triangular matrix.
upper triangular. Yeah. And also, if you are whatever the leading entry should be 1 in that case. Now let me show
So
the word
one more,
also. Yes.
sorry, sir.
I
One
will
more
I will
doubt, sir.
discuss. I will discuss the more question here. So let me read out this one. See that the row echelon form is a matrix in is called or you can say in the row echelon form if the first non-zero element, so the leading entry is in a row is 1. See that what I am saying here. Now let me write here or let me show you. So let me write as here this example. I'm taking this example. Okay. So this is you're going to be the word. What is the word? First non-zero element. Take the first in the first row. Okay. This is apply for any row. No? This is apply for any row. This word is apply for any row. So first non-zero element in a row. So see that in a row, not a first row. In a row, any row can be is 1. So here see that this is going to be your first non-zero element in the first row. This is where going to be the first non-zero entry, sorry, element, not entry. Non-zero entry in the second row. This is your first non-zero entry in the third row. And what is saying is the first non-zero here in place of element, it should be entry. So yeah, leading entry is there, okay, is 1. So this should be 1. So here should be 1. Here should be 1. The third row is fine. Now the next word is what? The column containing the leading one. Leading one means column. Column containing the leading one. So see that this is the row and this is this row for this one. What is the column? Leading one. Leading one means what? This row, what is leading one? This is you're going to be leading, right? For the third row, this is you're going to be leading. So column containing leading. So leading. So this is the leading column. Sorry,
So
this is the
when
column which contain this leading entry.
so when you
This
are
is the
seeing
leading entry.
this, it is not visible, sir. Your
Yeah, it's
marker is
invisible. Whatever you're writing in notebook is not
So your
visible.
pointer is not visible where you are pointing.
Oh, where I'm pointing, it is not visible. Okay.
So maybe mouse can be useful.
if you
Okay. So
underline that word or
yeah, I will. That's why I will underline. So the third row, okay, this is you're going to be leading entry, right?
Yes, sir.
For the second row, this is your leading entry.
Yes,
For
sir.
the third row, this is your leading entry. And the first condition says here the leading entry should be 1. So let me make it 1. Anyhow, I will do the row operation and anyhow, I will try to convert this in 1. So what I am doing, so let me do here, I am dividing the row 1 with 2. So what you will get here, now I see that I converted this matrix in, this is 1 by 2 here. This is 0 and this is 1 by 2. This is 2, 0, 2, 1, 0, 0, 0, 1, 2. See, now in the second row, your leading entry is 1 here. But the second, sorry, the first row. In the second row is not 1. So let's again change it here.
sir,
So
when we change the matrix will be changed, no? With the original matrix
matrix will change. Yeah, matrix will be changed. So I am converting this matrix in row echelon form. So matrix is actually we are changing in the matrix. Okay.
Okay.
We are actually changing the matrix. So here is I when I divided second row. Okay, this is going to 1 by 2 0. This is going to be 1 by 2. This is 0. This is 1 here. This is 1 by 2 and this is 0. This is 0 0 1 2. Now it is fine. Now see that the first row is in leading entry, which is 1. Second row, the leading entry is the second row leading entry is this one and which is 1. The third row leading entry is this one and which is 1. Now the first condition have fulfilled. The first condition is fulfilled. Now come to the second. The column containing leading one of a row. Of the second row, leading one is leading entry is this one. And column, which column is? This is the column. This is the column. for the second row, okay, let me erase it here. For the second row, leading entry is going to be this one, which is 1, and column containing, this is your column. This column contain your leading entry. The second column contain your leading entry for the second row. Okay. And what it is says, column containing leading one of a row is to the right of column containing the leading one of the row. What it mean? It means says, let me erase it here. When you are changing your matrix, or when you, that matrix is this matrix C. This is your first column, this is your leading entry. So this is your column containing leading entry. Now when you come to the second row, then your leading entry should be right. That is the word here. Should be right of the column containing leading one. So this is your leading one. So in the second row, leading one is this one, and it is actually in the right. That is the word here is saying. Okay, this is the second container. Similarly, this is for the second row. For the second row, this is your leading entry. Now in the third row, it should be right. So this is, yeah, actually it is right, and it is the leading entry. The leading entry should be right of that column. So this is here. So actually it is following the row echelon form condition. Now
Sir,
let me
if
So
the second
suppose
row,
in the last
if the,
element it was not one will become one was suppose 0, then we have to convert the 2 into 1.
Sorry, which row?
Suppose in the given question that you are doing, suppose the last in the last row the third element is 1, right? Suppose it was 0, then we have to convert 2 into 1.
No, it is, if it is 0, it is still, it is fine. Okay, suppose it is 0 here. Okay, suppose it is 0 here. If it is 0 here, so yeah, here we have to convert. Here we have to convert it for 1. Yes.
2 will be converted to 1, or we have
1.
to convert 0
Here,
into
this
1?
one we have to convert 1. Because this
Sorry,
is
sir,
your,
bro.
for the third row. Yeah, just let me finish. This is your, in the third row, this is your leading entry, and it should be 1.
Okay,
That's the thing.
thank you, sir.
Yeah, hello,
Yes.
sir.
yes, sir, if in the second row, if the first entry is in the last column, then the last row must be 0.
Sorry, can you repeat again,
In
please?
the second row, if the first entry is in the last column, uh, so the last
Okay.
row must be a 0, all zeros.
Then in that case it should be 0. Suppose the case is here, this one is happening. Okay, this is happening. Okay, this is happening.
Also, can you please explain independent dependent variable with
Yeah, I
respect
will
to
tell you. Once it
review?
will finish, then the independent and dependent will come. Once you will know this one, then the independent and dependent will come. Okay.
Okay.
After doing this, we will discuss this. So it is 1 here. Then in third row, it means that all entries should be 0. All entries should be 0. Otherwise, it is not in the row echelon form. Suppose the case is here. Suppose the case is here. This one 0 is here, but here is again you wrote 1. So this is not in row echelon form because of second line. The second line says leading one of a row is the right of the column containing the leading one of the row above of it. So this is the leading one, above of this row is this one, and it should be right of this one, but here is not in the right. That's why it is not in row echelon form. Now
So,
let's talk about the third. Yeah, let me back to the matrix, original matrix. Yes.
so in case of zero matrix, sir, so how is it in row
Yeah,
echelon?
zero. In case of zero matrix is actually, you can say, in row echelon form. So I will discuss that. I will
Yes,
discuss that.
yes, sir. Yes.
So this is going to be your 1. This is 1/2, and this 0, and this is 1, and this is 2. So now let's discuss the third line. Any non-zero row are always, any non-zero row always above row 0 will, any non-zero rows are always above rows which with all zeros. Yeah, it means that suppose you have a suppose your matrix become this one, okay? Let me erase this one, and this is the thing here. All entries 0. For the second row, all entries 0. So this is not in row echelon form. If you want to make it row echelon form, you have to do extra operation that is called the first type, swapping. You have to do swapping. So swap, that swapping is represented by this one. So R2 swapped with R3. The representation for swapping is this one. So now once you will do the swapping, then it will become your row echelon form.
But the
Make
swapping,
all 0.
but
Sorry.
the swapping causes the negative sign.
But we are not mapping. We are not doing anything here. We are only just doing the operation and writing the matrix. We are not doing anything here. Not we are. There is no. I'm not doing here the sign also. I'm not writing the sign. I'm just doing the operation. That's why they see that this sign is there. This sign means it is not saying the exactly. It is saying the approximating. You can say this is usually this is indication of changing, or you can approximating or something. Right? This is the.
Okay, okay.
So
Thank
that's
you,
why
sir.
I'm not writing the sign here.
Thank you.
Actually, I'm here. Here the mean is I'm converting this matrix to some different form.
Sir, is it necessary that the leading element should always be positive one, or it can be negative one?
Always one. Always one. Nothing except that there is. If it is negative or anything, that should not acceptable for the row or even reduced row. Row echelon form or reduced row echelon form. Only one should be. Okay.
So just one question.
Hmm.
Sir, what is the difference between these two arrows, that straight arrow and this curved arrow? Like you are
This one and this one.
the S-shaped arrow
Huh.
between the two steps.
So mean is that I'm actually this is mean that I did something, and after I did this operation, okay, and after doing operation this is the indication that I got this matrix. Okay, this is just an indication. Okay, I did this operation, and after doing this operation I got this matrix. So this is indicating that I got this matrix.
And so
Okay, this is just indication.
so determinant changes, no? So when we divide,
Determinant change everything. Matrix even change, determinant even change. But see, I am doing operation, but yeah, determinant is changing. Something happened, but I doesn't matter. Actually, what I am doing, I am converting this matrix in row echelon form. That's all.
okay, thank you, sir.
Okay. So this is let me back to our original matrix. Then so this is our actually the row echelon form. Now let me add one extra thing. One more thing, that's enough to saying the reduced row echelon form. So let me back to here 0. This is 1.
Hello, sir.
Yes. Yeah. Hi.
If we have say upper triangular matrix, or sorry, if we have lower triangular matrix, then will it be a
No. Only this things. Only this one. Only acceptable for this type of. So if you are lower matrix, you have to some do operation and you have to convert that in. So lower matrix is not in reduced row echelon form. Okay. Only
so
upper matrix means upper matrix you are anyhow you are changing in this form. Not even the upper word is a proper word to use. Okay. Only you are changing this matrix, or in this form is actually called the row echelon.
so anyhow we have to convert it in this format only.
Yeah, anyhow you have to convert, or somebody's asked, no? If you see the activity question, in activity question have different type of matrix and asking that which one is in row echelon form and which one is
So
not in.
so can we always
Sorry.
convert it into a
Yeah,
suitable
any
form?
matrix can be converted. Any matrix can be converted in row echelon form and reduced row echelon form.
Okay, okay, sir. Thank you.
Now let me add one more extra
I
thing.
have a doubt in this.
Sorry.
Like
So,
when we are converting this, am I audible?
yeah, you are audible, but your voice is very low.
Sir, is it now okay?
Yeah, okay.
saying कि when we are doing these all row operations and everything, like I got to know that determinant will change, the value of determinant will change with respect to the operation that we are doing. But I am very confused कि how do we keep the list of those changes? For example, I've changed the whole matrix and at the end I'm just there to
You are
calculate the
listing here. You are listing
determinant.
here. This one. You are listing this one, no? I did operation. So this is the
So
list.
we actually have to list them down ताकि हमारे determinant की value change हो तो हम बाद में लास्ट में जाके change कर ले वरना
No, no. So forget about हम मतलब हम लोग को उसके determinant से मतलब नहीं. We are not considering. Only we are changing. We are not considering the determinant of matrix. Only we are converting our matrix. So forget about, in this case, forget about the determinant. Yeah.
Okay, sir.
Yes.
But sir, what is the need of converting this matrix to in this
Yes,
form?
I
Like,
will
why
tell
we
you.
are
That's the
converting
thing.
this
Here.
is
Why
it?
we needed this one. So we will use this one. If you see that Gauss elimination method is nothing but this kind of operation you are doing. What is Gauss elimination method? In Gauss elimination method, you are actually convert the system of linear equation in row echelon form or reduced row echelon form. Once you did that, it will give you the solution, and also it will tell you that it is a unique solution going to be or no solution or infinitely many solutions. That's why we needed this form. We will see the use of this type of, why we needed this form is actually we'll see in the Gauss elimination method.
So only
Okay.
row operation can be used. We cannot use column operations.
Yes, only row operation, no column operation, only row operation. That's why sir didn't teach actually the column operation, only taught row operation.
For in case of determinants, even if you use column operation, the determinant will not change, right?
In the case of determinant, it will be not change, but here it will be effect for the Gauss elimination or in the this echelon on row echelon form. Okay.
Sir, I had a few doubts in practice assignments.
Yes. What? Yeah. In practice assignment.
Yes. Sir.
Okay. Okay. Then okay. Let me finish it. Then it will be good to discuss that.
Okay.
Sir,
Okay.
what
Yes.
is the difference between row echelon form and reduced row echelon form?
Now I hope now the next thing is going to tell you the reduced row. So is it clear till now? I hope everyone is got clear, right? What is that row echelon form? Everyone got that? Anyone have doubt? Please let me know. I am here. I will tell you that what is your doubt. I will discuss that. Any kind of doubt.
Sir, in row echelon form, the pivots
Yes.
can only be one, right?
Only the one. Yes. Okay. Now let me tell you now reduce row echelon. It is nothing but only the some extra effort needed to do that. So what is reduced row echelon form is, see that here is actually this matrix is in row echelon form. Now this matrix in row echelon form. Okay. Previously whatever you gave me, it is not in row echelon form, but now I did some operation and actually this matrix in row echelon form. Okay. Now what I will do, so this is not in reduced row echelon form. This matrix is not in reduced row echelon form. So what is the reduced row echelon form? See the leading entry. Okay, this is my leading entry. Above that there is no row. Okay, so there is no need to talk about. But below of that there are rows. Okay, so below of that there are rows and actually 0. So it is good. It is fine. Now come to the next pivot element for the second row. This is our pivot element. Okay, this is the leading entry which is 1 here. Okay, now below of it is 0. Fine. And above of it there is one row, and when it is one row, it should be it should be 0. Okay, if it is 1 by 2, see it is non-zero, then it is not, so it is saying to be this is not in reduced notion of. Okay, now come to the third row. This is our pivot element, this is our leading entry. Okay, I think it is not properly written. This is 1 by 2, here is 0, no, our 0 is here. Okay. So this is our 1 here. Above that there is, below of it there is no row, so there is no issue. But when you are going above, okay, So this should be 0 and this should be also 0. Then our matrix is going to be reduced row echelon form. See, this is our not leading entry. See, this is not our, this 2 is not our leading entry. So below of it and above of it, we will not discuss. We will not even discuss that. If it is leading entry, then we will discuss. See that this is not our leading entry. So what is above 0 is there, 0 is not, or 0 is above the row is 0 or not. It doesn't matter. Only matter for the leading. Only for leading entry we mean it matters here. That we want 0 there. Above and below should be 0. See that word here for the reduced row echelon form. If you see the word, first line is the same for the in the reduced row echelon. This is for the word for the reduced row echelon form. Okay. See the first line, both have the same first line. Okay, first non-zero element in the first row is 1, as here is 1, is the number 1, the same word. All subsequent non-zero rows must also have their leading entry as 1, and they should appear is to be right. This the same word is actually. This word is actually the same. Only the, see here in, if you see that in this row echelon form, only 3 things are there. 1, 2, 3. But in reduced row echelon form, one extra thing is there. This one. The third row, if you see the this third condition is also the same. Any non-zero row always okay. So the fourth row here is the fourth condition. In this fourth condition is the third condition. Only the third condition is extra needed we for the reduced row echelon form. What is the extra thing? The whatever I am saying, above and below should be 0. See, let me read out. The leading entry in each row must be only non-zero number in that column. Okay, and in the second condition is actually mixing with that. This should be 1 and above and below should be 0. 1, and they should appear to right to a leading entries in the previous row. Okay, the first non-zero in the row is 1. Okay, the leading entry in each row must be only 0 number in its column. Any non-zero row are always okay. Any non-zero rows are always above the zeros rows. Here is, I think, missing the word or no? It is the first non-zero element in the first is 1. Okay, all subsequent non-zero rows also have their leading entry. Okay, the first non-zero entry as 1, and they should appear to right of the leading entry in previous row. The leading entry in each row must be only okay, this word is the leading entry in each row must be only the non-zero number in its column. So here is the leading entry and non-zero number, and this is, and the corresponding column is this one. So only this one, in this column only the leading entry should be non-zero and rest all should be 0. Rest all, this one should be 0, this one should be 0. For this one, this is going to be your leading entry, and the corresponding column is this one, and in this column except this one, rest all should be 0. This is the mean. This is the third line it's saying. Okay, so now let me tell you, now let me open the question, okay, of activity of the, I think this one, I think, okay, now it will be more clear when we'll discuss a question. In this question, not in this question, let me open the echelon for reduced echelon.
So open the previous one, echelon form first.
Yeah, I think this one, yes. Echelon form. So now see that we have different kind of matrices here. Now tell me which one is going to be your row echelon form and which one. So let me discuss the matrix A. Is this matrix A in row echelon form?
No, sir.
No.
No.
So let me tell you that one thing. A matrix is in row echelon form. No, a matrix is in reduced row echelon form is actually in row echelon form. Okay. If a matrix you have, it is in reduced row echelon form. Okay, reduced row echelon form. Then it is actually in row echelon form, because reduced row echelon form needed extra effort. Okay, we did an extra effort, then we are saying. So every reduced row echelon form is in row echelon form. So what you can say, if a matrix is, so let me write here, if we reduced row echelon form matrix is row echelon form, is in is in row echelon form. Okay, but converse is not true. Okay, if matrix is not in, so differently also you can say, if a matrix, okay, is not in row echelon form, okay, then it will never be in reduced row echelon. Then it will never be in reduced row echelon. Okay. If a matrix is not in row echelon form, then it will never be in reduced row echelon form. Okay. And the first case is every reduced row echelon form, or you can say if a matrix is in reduced row echelon form, then it is in a row echelon form. So reduced row echelon form is needed extra effort, extra condition also. While while looking this condition, you can see that whatever we discussing, reduced row needed 4 condition, and row echelon form needed only 3 condition. So that's why you can say every reduced row is actually in every reduced row echelon form is in row echelon form. Okay, now, so this is in not this is not in row echelon form, so it will never be in reduced row echelon form. What about this B?
Not, sir. Because
This
leading
is
entry
not.
is -1.
Yes, this is in the first row. This is your leading entry, -1. In the first row, -1 is going to be leading entry, but no, it is not in. It is not 1. It is -1. So this is not going to be your row echelon form, and that's why it is not. It is not going to be in reduced row echelon form also. Now, what about C?
Yes, it is, sir.
It is
And
in
it is
echelon
row
form.
echelon. What about reduced row echelon form?
No.
No, it is.
Yes, sir, it is.
It is in a reduced echelon
Yeah,
form.
it is in reduced row echelon form also. Why? Because see, my cursor is able to see, right? This one is.
Yes, yes.
Yes, sir.
So this is 1 here. Below of it is 0. Fine. Now come to the second row. This is the leading entry. Below of it and above of it. Okay, below
0.
of it 0. Fine. Now come to the third row. There is no leading entry, so no need to talk about. Only till third one is fine. So this is in actually in reduced row echelon form. Now what about the D?
Yes, sir.
Yes, it is.
Reduced row.
There is no entry, non-zero entry. See, these conditions are only apply for non-zero entry. Okay, but here is there is no non-zero entry, so it is automatically in reduced row echelon form and row echelon form.
Yes, sir.
Please, if you are muted, somebody's background noise is there. Whom? From whom? I don't know. Okay, please unmute yourself. Okay. Let
Sir,
me.
by that method, identity matrix will always be in reduced row and
Yes,
row echelon
yes,
form.
yes, yeah. Identity matrix is actually reduced row echelon form, and in reduced row echelon form. So that's why it is in row echelon form. So what about the third? Sorry, third means here. Sorry, E. What is E? What about E?
So can we
Sir,
say
it is.
that what
It
we
is
are trying to
echelon
make
form, but not
It
in
is not.
reduced row echelon form.
No, it is not in echelon also.
Yes, it is not in echelon form also.
So can we say that whatever we are making it like raw echelon form, it is only the identity matrix that we are going to make out of it. So it's just a name that we are
No,
giving it.
so the thing is, if your matrix is a square matrix, okay, if your matrix is a square matrix, so then there is a possibility that the reduced row echelon form of that matrix is can be identity matrix also.
Not possibility, sir. It is 100%.
No, it is not necessary. Suppose you have a matrix, when you convert it in reduced row echelon form, it could be for zero
Sir,
matrix, it will say for zero matrix, it is in reduced row echelon
yeah.
form. Is this
Except
identity?
no, no, no. Sir, except
Okay,
0,
okay, got it,
all
sir.
will be
So
identity.
identity matrix is only a square matrix, and echelon form can be any matrix that we are making.
Echelon form can be, yeah, any matrix. Only identity. So the thing is, then I can add here the one extra condition. Then if your matrix, the determinant of matrix is non-zero, no. So in that case, reduced row echelon form is for that matrix is going to be identity matrix. I said right, reduced row echelon form is unique. Row echelon form is not necessary. It can be different also, but reduced row echelon form for a matrix is unique. So suppose if you have a matrix which have non-zero determinant, when you calculate it, you got non-zero number. In that case, you're when you're converting that matrix in reduced row echelon form, then you get identity matrix. So what about this E matrix? E is not in row echelon form. The reason why? Can you tell me?
Sir, the
Because
second column.
because sir, in each row numbers of zero must be more than previous row.
Yes, yeah, that is one easier word to say. And also it should be in the sequence wise. Then
Yeah.
yeah, so you see that it is one here. Okay, yeah, actually it is one here. Below of it should be zero, but here is not. Here is one, not zero. That's why it is not. So it is not in row echelon form. Then it is not in reduced row echelon form. What about this one?
Yes, it is in echelon form, sir.
Echelon form. What about
Strong.
reduced row?
Not
Not
No,
in
no, it
reduced
is
row.
not a reduce.
The same, yes. What about this one? G?
Yes, it is. It is echelon form,
It's in
but not
reduced
in
echelon.
row, not in
But
reduced
not
row.
in reduced row.
Yeah,
Yes, sir.
yeah, right.
What about this one? H?
So this is both
It
echelon
is
and
in both.
reduced.
Yeah.
Reduced
What
row.
about this one?
This
No,
is
sir.
not.
Because the
Not
sign
in
is
This is
negative.
not.
echelon
Both
form.
knobs
Yeah, both not because of, yeah, this is because of minus one. What
and
about this one?
both yes, sir.
Yes,
Both,
sir.
Reduced.
both, yes.
Yeah, it is fine. Identities, we already know it is, yeah, fine. What about this one?
Yes, sir.
Ah, what about this one?
Yes,
Uh,
sir. Reduced question.
yes, it is. Yes, it is in.
It is both. It is
No,
both.
not
Both.
both.
It is both.
Okay, okay.
Yeah,
Third
both.
row is
If
not.
there is
Third
minus
column is
one
not.
here,
Because
so
Yeah,
we
no.
can make it reduced.
This
sorry,
is
sorry. Now
echelon
I'm
form
yeah,
only. This
one by one. Yes. What is that? It is both. I'm saying it is both. Why it is?
So
Or
like
anyone
minus
have doubt
two
that why
because
it is the let me so please let me know.
yes,
What's your doubt?
yes, sir. I'm saying कि it is reduced echelon form में isn't it minus one a problem here?
No, so minus and one is, see, this is not your leading entry. This is your leading entry. So this is your
No, sir, I'm
leading
talking
entry
about the
and
reduced.
sorry,
Sir, reduced.
There is no
There is a
leading entry in
reduced.
column 3.
column three is no column. We don't see. That's why I said no. Let me tell you here. It
Yes,
doesn't
sir. There is
matter
no
here.
entry in column 3, so we are not seeing anything
Yeah,
on
Here
in
are
yeah,
column
only
3.
two
yeah.
leading edge, two
Yeah,
leading
only the
entries.
leading actually, only the leading, only for leading we
We
concern.
are not considering.
Below of and below and above should be zero, but this is
So for
not your leading.
reduced echelon form.
Yes, so that's why
So
it
for
is in
reduced
reduced both.
form.
Sorry,
So both.
yeah, this is both. So now I think now let me tell you the independent and dependent variable here. So this is only simple word, only in one word you can understand. Take this one, okay? Take this one. Okay, it's better to be let me write here the same matrix. Okay, 1 0 minus 1 0 1 1 is here. suppose this is a coefficient matrix, okay, coefficient matrix of a system of linear equation, okay. So can you tell me that, so I'm saying this is a coefficient matrix, so let me write the system of linear equation, okay. So forget about, I don't care about the right side, only this one is
Sir,
enough.
it will be three. There will be three.
So yeah, that's I
rows.
missed it. Here should be three variable, then the matrix
Yeah.
multiplier, yeah, that's the thing. It is good to you said. So it should be three variable. Now if it is there, so let me write here. So either I can say this can be multiple, so this could be converted in system of linear equation also, right, in the equation form. What is going to be this one? X, let me write here a, b and c is here. Suppose right side is this a, b, c. What is going to be your matrix, sorry, equations?
Sir, x minus z is equal to a.
X
A.
minus,
Yes. What is going to be the second?
And y
y
plus z
plus
is equal
z
to.
is equal
Y
to
plus z
Oh,
is
I sorry, I this is not here one here, sorry. This is not going to, sorry, here is not going to be C. I missed that.
Yes, sir.
Okay, this is whatever this one is going to be this one. Okay, so this is y plus z is equal to
Is
b.
equal to b.
So see that, suppose I said, right, this is in reduced row echelon form. I said that this is a coefficient matrix, so this is going, suppose this is the system of linear equation, so we got this one. Okay, now except writing here, suppose I am writing here. So suppose so this is not taught in video lecture. This is not a right way to writing here the variable. Only this, only for the, for time being I am saying, suppose I am writing here this x, y and z here. Okay, now see, this is your leading entry, this is your leading entry. So leading entry keeps the independent variable, and non-leading entry gives the independent variable. Now can you tell me which one is going to be your independent variable and dependent variable?
Z is
Sorry, sir, I didn't get.
independent. X and Y is independent.
Please
Dependent.
repeat what you
Sorry,
told.
I wrongly word used just now. I think I used a wrong word. So
Sir, please repeat what you told.
yeah, I say I actually used the wrong word. It is, let me tell you that leading entry give the dependent. Okay, dependent. This is your leading entry, this give the dependent variable. This is your leading entry, this give the dependent variable. And which one is not leading? So not leading. So for this one, for this variable, there is no leading. So that's why it is going to be independent. Okay, and both is here is going to be dependent. Is it clear now? For Z, there is no
Yes,
leading, so it is going to be independent. But for the leading one, we will get dependent variable.
This is shortcut method, sir, to identify which one is dependent.
Yeah, it is easier to, like, always many of
So,
like,
sir,
yeah.
is it necessary that the leading entry should be one?
Yeah. So the concept of independent and dependent variable, when it is come after reduced row echelon form. So you cannot decide without converting your matrix in reduced row echelon form. Once your matrix, once you converted your matrix in reduced row echelon form, then you will get no leading, non-leading. So without this, without, so once your matrix in the reduced row echelon form, in that case you will only decide the which one is going to be dependent variable and which one is going to be your independent variable. So reduced
Sir,
row
in
echelon
that
form is
case,
great. Yes.
sir, in that case, so we already have a matrix in reduced echelon form. So our dependent and independent, both the variables would be either 1 or 0 or minus 1, right?
Sorry. Sorry. Can you repeat? Could you repeat?
Sir, I'm saying ki, we are saying these dependent and independent variables only after doing and making it in the reduced echelon
Reduced row
form, right?
echelon form. Yes. Yes.
So in that case, both are dependent and independent, or dependent or independent, both will be 0, 1 or minus 1, none other number than them.
No, it is not necessary. Some numbers also. Let me now let me give an, let me take an example and tell you. Suppose I'm suppose you have a system of linear equation this one, okay. Let's say 2x plus 3y plus z is equal to 1, okay, and 3x plus minus here, let's say here is minus 2y plus 3z is equal to, let's say, 2. Okay, suppose you have this system of linear equation, and the question I asked that which one is going to be dependent variable and which one is going to be your independent variable. Can you tell me? So what is the process you will do? You will write
First
in the
convert it into
matrix.
the reduced echelon form.
So yeah, so write this system in the matrix form. This is going to be 1, 3, 2. Sorry, this is -2. This is 3 here, and this is x, y, z, and this is your 1, 2. Okay. Now change your coefficient matrix in reduce row, not even row echelon form, reduce row echelon form. Okay, so this is how we'll do this. So do the operations. What are the operation we will do? I want to make it here
First
1.
dividing by 2.
So
Do 1
R1
by 2.
divided by 1 by 2. So this will become 1. This is 3 by 2. This is 1 by 2. This is 3 here. This is -2, and this is 3. I just took the coefficient matrix. Now I did operation 3 times R1. Sorry, here is not this one. Okay. From the row 2, I multiplied 3 minus 3, or you can say I multiplied 3 with R1. Okay. In the row 1, I multiplied 3 and subtracted, because I want to be here 0. So let's make it here 0. So this operation I did. It means that this is the same 3 by 2 and this is 1 by 2. I multiplied the first row with 3. So multiply and subtracted with the second row. So that's why it will become, see that what is 3 times minus 3 minus 3, it will come 0. And this is here -2. Multiply with 3 here, it will become -9 by 2 here. Okay, this is going to be 3 minus 3 by 2. Clear? So the thing is here 1, 3 by 2, 1 by 2, and here is 0. And what is going to be this one? This is -13 by 2, right? And this is 6, 3 by 2. Again, you will get 3 by 2. Is it clear? Now, I got this one. So without the operation, okay, I just now do the next operation. I want to make it here 1. I have to make it here 1. So what you can do? R2 divided by -13 by 2. Okay, so what you will get here? I am writing here. Here is 1, 3 by 2, and this is 1 by 2. Okay, this is 0. This is going to be your 1. And what is going to be this one? 3 by 2 upon -13 by 2. Right. Now, whatever you will get, okay, fine. But here I want to, because I am changing in reduced row echelon form, no. So here anyhow I have to make here 0. Okay. So the operation now we will do R1, right, minus 3 by 2 R2. Is it clear? Is it clear? What I am doing here?
Yes,
from R1, from the row 1, I am subtracting after multiplying in row 2 3 by 2. So this is going to be 1 here. Once you multiply here, so once you multiply here 0 with 3 by 2, it will become 0, and subtract, it will be the same here. Once you will do here, it will become 0. And I don't know what suppose this is going to be your 1 by 2 minus some number will come. Okay, I am leaving it here. But yeah, I actually got the reduced low echelon form. So this is going to be your 1 and some number. This is the same number will come. And here is some number will come.
So, sir, converting into row echelon form, so we can do only the row operations.
Only row. Only row operation.
We cannot.
You cannot do the column. Sorry. Yes.
So,
yeah.
So I'm saying that this is what I was asking ki when we are having this reduced echelon form, so we are having some numbers as well. So it is not necessary that in reduced echelon form we only have a matrix consisting of 1, 0, -1. There can be some numbers as well.
Any number, only the leading entry one. See that this one is not leading entry, so it could be anything, and it is not any. There is no any problem. There is nothing. There is no.
Then why 3/2 was converted into 0? It was not the leading entry as well.
3/2 is
No,
converted
there
to.
is there is a leading entry in the column 2.
No, so in the column 2 here is 1. That's why I converted here 0. No, I am actually changing in the reduced row echelon form. No, so to changing in reduced row echelon form, here is 1. So I have to make it here 0, right? That's why I
Okay. So
multiplied.
above, so column wise, above and below the independent variables, there has to be 0.
0
Apart from that,
in
like
reduced row
in
echelon.
the column 3, there is no independent variable or the leading value, so we will not convert it, leave it just the
So
way it is.
these leading entry will not give the independent. These give the dependent variable. So now see that what is happening here. This is x y z here. Okay, this is our system of linear equation. In place of writing for the, if you want to very much like we want which one is going to be independent, right here x y z here. Okay, now this one is leading, so that's why x is going to be dependent. Here is leading, that's why it is going to, y is going to be dependent. But the third row for the z, there is no leading. That's why z is going to be independent. Okay.
Sir, it is not taught in the lectures.
No, dependent and independent taught in lecture.
Nice,
It is there, not that much explained. And one more thing, sir.
Actually, sir is while writing that PDF is just sir is the reading that PDF and said that okay, this actually this is why I am saying this is easier way to get that. That's all, and nothing else.
Sir, can you please explain the reason behind this? Why this is called?
So why it is
dependent
called
and
independent? Yeah, the reason behind it. Now, can you tell me? Now, see, you have a reduced row echelon form, no? So, can you tell me what is going to be the system of linear equation after changing the reduced row echelon form? What is going to be?
X.
Variable or
X.
rise to variable from 3.
That some number, no? I
That's-
don't know what is number. Let's say that number is alpha. Let's say this is alpha. Some calculation is there. I don't want to that calculation. I don't want to calculate it. So let's say this is alpha. So alpha time what will come? Z. Right? So it is minus I am writing, you know. So not minus. I don't know what is alpha. So let's better to keep it plus. Okay, this is plus. So alpha time plus. It is going to be what?
A.
1 something.
So 1 will come. So that's why the Gauss
Any
elimination.
constant.
That's why the any constant. So any constant, because
A.
that's
Let's
why the
suppose
Gauss
A.
elimination is come. Let's say this is A. Let's say A. Because
Yeah.
when you do operation, no, so both side you have to do.
Yeah.
So that's why let's say this is A here. Now what is going to be second? Is going to be
Y
plus
some, let's say this is beta.
Beta
Z is equal to, here is, let's say B.
B.
Right side. Now see that what is happening. Now change this. Okay, what you will get? X is equal to A minus alpha times Z. Y is equal to what? B minus beta times Z.
Yeah.
So this is your solution. You can give Z to any real number and you'll get the, so this is the mean here, infinitely many
Yes.
solutions.
X is dependent on Z.
X is dependent on Z. See what we got here? Z is independent, X and Y dependent. So what is happening here? X is dependent on Z and Z is actually independent. Y is dependent as here because of leading, and this is going, Z is independent. That's why it is Y is dependent on Z. That's the
Sir,
meaning
we
here.
can also
Dependent.
write. Sir, we can also write Z is equal to X minus A upon.
Yeah, that would be. That
plus
is
A
possible.
upon alpha. So
You
Z,
can write.
why both are dependent on each other? No?
Both are dependent on each other, but see that, but see here in the case of, in the separate equation you are saying, but when you combining these two, then what you will say?
Sir,
In one word.
Sir, you multiply
Yeah.
1 by alpha to both sides. So Z will become
Not
independent.
I didn't multiply it. That number is actually that number I'm saying alpha. I didn't
But,
multiply it here.
but equation will not change. No, sir,
Got
if
it, sir.
equation.
Understood.
So see that
Sir,
it is single. It in the single equation it's look like either Z and X can be dependent and independent, but in the system it is independent. See, you are saying Z is dependent on X. Okay, fine. But Z is dependent on Y also. But what you will say in the single word? In the single word, I want words. In single word, I want. So in the single word, you will say Z is going to be independent, and it's better to say Z is going to be independent, and X and Y are going to be dependent. Is it clear? In the
Basically, which
single
is
equation,
Yeah,
it
yeah.
looks like.
Yes, sir.
so
Got it.
basically the variable which is common in both x and y will be independent.
Independent, right?
We
This
can
is the
say that
meaning.
a common variable will always be independent
Yeah.
in the given set system of equations.
yeah, okay.
Okay,
Yes.
Yes,
clear.
sir.
But
So this
sir,
is the
there
story
is a
of, yes.
situation.
So if one variable is more than if a variable is present in more than one equation, then it is
Going to be
then it
your
is
independent. Yes.
independent.
Sir, if it
Yes.
was a 3 by 3 matrix, then Z may or may not have been independent, or
Yes.
it should always be independent.
No.
Or
If
sorry,
it is
dependent.
a 3 cross 3, then there is a possibility. No, system has unique solution. In that case, what? System has unique solution. So in
Z
that
should
case,
be
if you
dependent.
change your coefficient matrix in reduced to echelon form, it could be identity, right? Identity matrix. So suppose you have a system of linear equation. So let's say this is okay. This is your system of linear equation. This is your matrix. When you converted this matrix in reduced row echelon form, you got identity matrix, right? You got identity matrix 1 0 0 0 1 0 0 0 0 1. Now write here the variable x, y, z. See that what is happening here. For leading one, this is dependent. For leading one, this is dependent. For leading one, this is dependent. All three are dependent. What do you mean by dependent in that case? In that case, you are getting unique solution. And actually, it is all are depending in real number, unique number. That's the meaning of independent.
Okay, it means if all the
Could you, no,
three
sir?
variables are
Could you,
dependent, then it will be a unique solution.
Yes, if all variables are dependent, then it is have unique solution.
Okay, unless
could you repeat
suppose if
again?
there are more than
Means,
one, then it will be not having unique solution or no solution.
Yes. In that case only.
Sir,
Yes.
sir, in earlier case, we thought that x was dependent on z, but here no variable is dependent on any other variable. Every
Yeah, another
variable is.
variable. So no variable is dependent on any other variable. That means each variable have some unique number. Each variable is
So
actually
each
dependent on some
variable
real
is
number.
independent.
Hmm.
So can't we say each variable is independent at its own?
No. So numbers are not how. What do you mean by independent? Independent means free. But here you is specifically giving some value, right? X will get
We are
some
getting
value.
the solution of x, y, z.
Yeah, y
Unique
is
solution.
actually will get some real number, some value. Z will get a real value. So
Yeah.
it is so x y z is not independent. It is actually dependent. They are getting some real value.
Sir,
Sir,
is it
by that
possible that
logic,
all the
Free.
three variables
by
can be
that
independent?
logic, the previous in the previous example, the z should also be dependent because it is also getting some value.
Yeah. So z is we are actually assigning some real number. It can take any real number. That's the meaning here. Free or
But
independent.
why we,
So I'm not
if
assigning. So so that's why when you come, so these questions will be now. I will stopping here. I am starting the discussion here because these things now will be answered in the when you will in Gauss elimination.
okay.
Sir,
Gauss
I want to
elimination.
ask if suppose all the three variables are independent, then it will be
Hmm.
condition of infinite solutions.
All variable will never be, all variable can be independent also. Suppose your system is 0 0 0 x plus 0 y plus 0 z is equal to 0 0 for this system.
No, my question is, if that is the situation, then the number of solution will be infinite or no solution?
In that case, even if
Infinite.
there is one single independent variable, no, in that case, system has infinitely many solutions.
And what will be the condition for no solution?
For no solution, so that's one thing. Let me tell you, even if such case happen, no, so even the system has infinitely solution or no solution. There are two possibilities. So that's why I'm missing here the word. If such case is arising, so in that case, system has either no solution or infinitely many solutions.
So that is
Sir,
homogeneous
if the
system that you are talking
coefficient
about.
matrix is in reduced row reduction form, then there will not be any case where no solution is there.
No, so now that's the thing here. Now we'll discuss in the next session when we'll say the system has no solution, when the system has infinitely many solution. And for the unique, we actually discussed. For unique is that each variable will be dependent. Okay, but
No, I mean, sir, if we have converted the coefficient matrix into echelon form, then that case will not come. That no solution is there.
Also, yeah, actually,
We have already catered for that.
one thing I also missed that even the all variables will be dependent, no? So in that case, even it may not have a unique solution. Means either in that case, there is a possibility that either it have a unique solution or no solution also. So let's leave it that because we'll discuss in the Gauss elimination. There are so many things are there. It still remain to discuss in Gauss. So we did
Sir, I
actually
want to
till.
ask one thing.
Mhm.
Suppose the system is homogeneous. Okay.
Huh.
So in that case, there is always one trivial solution, that is 0, 0, 0.
0, 0, 0.
So in that condition, there will be never be a unique solution.
It could
Oh,
be
sorry.
have unique solution. Suppose your coefficient matrix is invertible. In that case, the system has unique solution, only zero solution.
Even in case of homogeneous system.
Even in case of homogeneous, I am saying. In case of homogeneous, coefficient matrix is invertible, means determinant is non-zero. In that case, your system is going to be unique solution and zero solution. You can usually see it here, how it is. You are saying this one, no? This one.
Right, sir.
And suppose your A is invertible. So that means you can multiply inverse both sides. See that. This will happen.
So in that case, it has unique solution, but only one solution. I mean, solution is fixed. X, Y,
Solution
Z
is fixed,
equals
only
to
zero
0.
solution.
Okay.
Yes.
Sir, can you please explain 2.3 question number 9 and 10?
Yeah, now let's discuss because now the last lecture I am leaving for the next for the next
Sir, just look
session.
at it and give me a hint.
Yes.
I will
Now let's
solve it.
discuss your doubt. Anyone have
Sir,
doubt?
can we leave now?
Sir,
Yeah, if
2.3 question
anyone
number 9
wants
and
can
10.
leave, you can leave. Anyone want to leave can leave because now I will take the doubts. Almost
Okay,
whatever
sir.
I want to discuss in this session, I have discussed all. Till reduced row I want to discuss. I hope I have discussed. Maybe in the
Yes.
next lecture I forgot to finding how to find the inverse. Maybe I will discuss and then Gauss elimination. So
Sir,
maybe Lavanya will
2.3.
take. Okay, Lavanya will discuss that. So she can tell you.
Sir, 2.3 question number 9 and 10.
2.3.
Sir, what about the PA questions I asked earlier?
Just a minute. Let me finish it then. Which question number?
9 and 10.
Okay, 9 and 10. So choose the correct option. Hint, please read out the hint also before I will say reaching to the options. For the first option, okay, some options are here. Find out the adjoint matrix of an arbitrary matrix, okay, take a matrix and find out its adjoint matrix. Okay, arbitrary of a triangular matrix. Okay, what is saying? What's your
Sir,
doubt here?
why third option is not correct? If A is equal to A inverse, let's suppose identity matrix. That
Then determinant may not be one, not necessary. So you can think. You can think. Uh,
can you
you
give me
can
counter
take this one with
example?
an example. Yes, counter example will be okay. A If A equal to A inverse, then you are saying determinant of A equal to 1. Okay. If this is A equal to A inverse, what it mean that? Okay, so we'll tackle with the counter example. So example is, you can think.
Without counter example, we cannot solve this.
No, you can actually solve. Okay, just a minute. Okay, this could be for the -1 case. What is the inverse of this one?
Same matrix.
Same matrix. And what is the determinant of this one?
1.
1 is here. Okay. Okay. Also, I forgot that. Then what about this one? -1, 0, 0, 1. What about this one?
-1 determinant -1.
-1 is determinant. What is the inverse of this one?
Same.
Same. Now see, the determinant is -1 can possible, and you are getting same inverse, and A inverse is same.
Yeah.
And what about the 10th question?
Yeah.
What is out here?
So this property,
Third.
This is property or something else? We cannot.
Yeah, these are the property of adjoint.
This has been not taught in the lectures.
So no, it is taught in lecture. It is in the inverse that which I left. This I forgot to discuss that in inverse of that. Sorry, this one in this invertible coefficient matrix. In that you will see the how to find the inverse. How to find the inverse is actually uses the adjoint. So suppose you have a matrix, no? So if you want to find the inverse of a matrix, what is the process? In that you will first find the adjoint. So what is the formula? Actually, we will say inverse is equal to
1 upon determinant.
Adjoint of matrix A and determinant of A. That is called determinant. Okay. This is, so see that this is adjoint here. So that adjoint is actually we use this in that question. Actually, we meant to discuss. So I will suggest to the next who will take the session, Lavanya. We'll discuss about the inverse, how to find the inverse, and then the Gauss elimination.
Sir, in matrix multiplication, A into B, and
yes,
the not is equal to B is equal to A. B
A into B is not necessarily B into A, but determinant will be the same. And adjoint. What about the adjoint? Adjoint of AB is actually adjoint of B into adjoint of A.
So how we can prove this?
So this could be proved because of, so once you know the how to find the adjoint of A.
Yes.
What will be the adjoint of A?
First we take minus and we'll take cofactors, and
yeah,
then we will
first take minus and then they write the transpose of in the transpose form, right? The row wise written in the column wise, right? You will
sir,
take
how, sir, can you explain?
Thing is, suppose you have matrix, let's say you have this one, okay? Suppose you have matrix A, B, C, D, and you want to find the inverse of it. So first find the determinant of this one. Determinant of this matrix is what? Let's say this is A.
AD minus BC.
AD minus BC. Now, what will be the adjoint? First, you have to find the adjoint of A. What is going to be adjoint? Adjoint is actually write the so you have to find the
cofactor of transpose.
Cofactor. First find the cofactor, then transpose it. So what is going to be for A1 cofactor? For A, cofactor is going to be D here. Okay.
For
B,
A, cofactor would D.
And for A, it is going to be minus C. For C, it is going to be minus B. For D, what is going to be?
A.
So find, and this is the transpose. Okay, so this is going to be your D minus C minus B A. This is your end joint. Okay, so we see that because of this transpose, actually, because of this transpose, we are taking the transpose. No, because of this transpose, actually, adjoint will communicate. See that. Oh, see what is the reason is. You know, right? AB transpose means what? B transpose, A transpose. Is it clear?
Yes, sir.
Are you right? You know
Yeah.
about this
Yes,
one?
sir.
So
Yes, sir.
what
It's
is happening in adjoint also? You are taking the cofactors, okay, and taking the adjoint. Sorry, in a transpose. That's why this is happening. You can say first find the adjoint and first multiply adjoint of B and then adjoint of A. Because of this transpose also, you can say. Okay, and a proper proof. Okay, maybe I will let you know how it will be proved. Okay, or also see that how it is. See, this one is okay. Using this one also, you can say. Let me first find the. Okay, what about inverse of AB? Okay, inverse of AB. Is it clear to you that AB inverse? What is inverse of AB?
B inverse, A inverse.
A inverse. Okay. What is AB inverse? Adjoint ADJ. Adjoint of AB upon determinant of AB, right?
Yes.
And this is what? Adjoint of B, determinant of B, adjoint of, actually this is the some, say, arranging or some equation manipulating something and doing this here. So this is the A here. Now this is, you want to find adjoint of AB is going to be your BA, you want to prove. No, so what is happening here? Adjoint of
Yes,
B
sir.
into adjoint of A, this is going to be your cancel out.
Cancel.
So that's why you can say adjoint of AB is equal to adjoint of B, adjoint of A. Another way also, by this way also you can prove using the inverse.
Sir, take determinant of A plus B. Please write determinant of A plus B is
Hmm.
equal to determinant of
No,
A plus determinant
not
of B.
necessary. Not
Not,
necessary. Not necessary.
but in case of adjoint, it is possible. It
In
is
case
true.
of adjoint, okay, adjoint of
A
A
plus B.
plus B. Yeah, it could be a adjoint of A plus B. So adjoint of A plus B is the
Adjoint of A
same
plus adjoint of B.
the same process if you will do here again. Okay. Okay, this is okay. If you will do with the here, okay, this is going to be A plus B inverse. So this adjoint of A plus B is going to be your, here is inverse of A plus B. It is not necessary that, okay. Adjoint of A plus B is going to be adjoint of A plus adjoint of B.
Sir, PA second question.
Yeah, okay, I will back to it. So actually for this one, I will see the proof and let you know. So that's why this is in the level 2. Actually, it's needed some search on Google. You can search the proof. You can see how we will prove. This time I am not getting that how to prove with this one A plus B. Okay, but let
Yes,
you
sir.
know. Okay, how we will prove it. The easier way, I will surely tell you how. The all things can be easily proved, but this time I'm not getting. Okay, we'll have to see it then. Let you know.
Okay, sir.
But
In next class, I will discuss.
these are all about in actually in level 2. If you are able to do the level 1, that's enough to do the core course. I will say whole course even I will say, or sub this maths too. Level 2 is some challenging. Who knows extra thing is good. It will be
Sir,
good.
Okay, sir. I will try and let you know in
Yes.
So
upcoming
where
lecture.
is level 2 means? Level 2?
Level 2 means the level questions are more tougher than level 1. That's why
In each activity
where is
there is
level
two
2?
level 1 and level 2.
if you see the in India activity, see this is level 1, and there will be some 4 to 5 question. Okay.
Okay.
Then you will see in the level 2. Level 2 is contain 2, 3, or 4, 5 question. It is actually challenging. You can say challenging problem.
Yes.
Sir, can you explain activity 2.68 questions?
Yeah, somebody is first. I have asked about the
So,
practice assignment. Then we'll back to
second,
you. Okay.
Okay.
PA, second question.
PA second question. So is this one?
Yeah, so the word problem.
So in this problem, you have to actually. So actually, the practice assignment is also till now when it is also have the due date. I think so, right?
Yes,
But for the hint, I can tell you that it's actually needed the Cramer rule to solve.
okay, Cramer. अच्छा. Okay,
Or
so
no, sorry, this is a simply a dare problem. Okay, so actually see, you know the quadratic equation, right? Or sorry, quadratic function
yes, sir.
in the maths one, from maths one.
Yes, sir.
So in maths one, the quadratic, so see that ax is nothing but a quadratic equation in x.
Right.
T is quadratic equation in x also.
So it
So
is linear equation. Tx is
ax
a2.
is quadratic, yeah, t is linear. Sorry, t is linear. So it is actually what is here. You need to solve the quadratic equation and put the value in place of x. Similarly, a2 t have to solve and put the value in place of x. You will get an equation. The system of linear equation will go. You will get a system of linear equation in a1, b1, c1, a2, c2.
Okay, so I'll try that.
Okay.
Thank you.
Try it. So yeah, somebody said ask something. Oh, what's your doubt? You can ask now.
Activity 2.68 questions.
Yeah, 2.8. 2.8.
2.6.
2.6. Question number 8.
Yes.
This one.
Yes.
So you have a system of linear equation. Then A is invertible matrix. Then the system has no
Sir,
solution.
eighth questions.
Sorry, this one. Okay. Suppose P is in this form where Xn is a defined matrix defined by the recurrence relation by this way. What is the sum of the all element of X0? So this is just a multiplication using this one. In place of, if you want, you write here. Okay. So what you will get? P of X0 is equal to X1.
Oh, yes. Sir.
And if you substitute here P of n is equal to 2, then P of X1 equal to X2. Right?
Yes. Yes.
And X2 it is given, already given. Can you,
Yes.
so you have X2 is given, can you backtrack again? Like after solving the equation, you can reach actually this, you have some extra, like X2 is given, you have to backtrack. And then slowly you can reach to find the X0. Getting? That means, let me tell you that you have P xn minus 1 is equal to xn. Yes? So P of, if you have substitute n is equal to 1, then what you will get? P of x0 is equal to x1. P of n is equal to 2. P of x1 is equal to
X2.
And x2 is given here. What is given here?
Yes. Yes, sir.
7, 8.
In place of x1, what we need to substitute, sir?
So for that you have P is given, no?
Yes, sir.
So P is what? Some equation, some matrix is given x1, and this is 7, 8, 3.
Yes, sir.
So you need to solve it, right? You have to solve. Once you solve, then you'll get that x1.
Okay, sir.
Again for this one you got x1. Again substitute here. You can solve and you will get x0. So that means I am meant to say backtrack.
Understood.
So can you give me one
Thank you, sir.
last hint?
Yes, sorry.
Can you give me one last hint for the 7th question in PA?
Seventh question. Okay. This is exactly same. This is uses Cramer rule.
Okay, for this. Okay, so I'll try that.
Yeah, just try it. Once you apply the Cramer rule, no, so you will easily get that. Just sip that. If you Cramer rules means what? You see that you have value x2 is here.
Yes, sir.
And if you use that to finding ax2, ax2 is nothing but what?
5.4.
That while finding ax2, you can use this one, no?
Yes, yes.
So use Cramer rule, you easily get that.
Okay, sir. Thank you.
Okay, so anyone have doubt? Please let me know. Now I'm going to close the session.
Sir, before you
Yes,
close,
Manish. Yes.
the one which you were just explaining, the use the Cramer rule.
Yes.
Can you just show me just first and second step only?
Sorry. One step.
Yeah, first and second step only.
So Cramer rule is nothing but, if you have a matrix is this one, let's say this is x is equal to, let's say b is here. Okay. Or let's say here is, let's say a and b. I'm writing in column wise. Let's say this is a11, a12, a21, a22. So so Cramer rules is just change this one with this column, and the x here is xy. So x is equal to determinant of matrix a b a12 a22 upon determinant of our original coefficient matrix a11 a12. Similarly for y, change this one and keep it is as the same, change this one with this one. This gives a y.
For y, you change the second column
The
of
second
matrix,
column,
right?
yes.
And by the b value.
Yes, by the b.
Okay. Wonderful. Thank you very much, sir.
So thank you so much for joining. I hope many of your doubt have cleared.
Sir, in practice assignment 9th question, can you give me a hint, sir, please?
So the thing is, we don't want to discuss the 9th question is the same. This is just now we discussed. No, this is total. It is exactly the similar. See, whatever we just now discussed, the activity, no, backtracking. I just now discussed backtracking. This one.
Yes, sir. Yes. Okay, sir.
This is exactly the similar. Actually, it is solved. See, that question is actually we kept here because of see that this is the equation. This is similar. Backtrack.
Yes, sir.
Okay.
Okay, sir. Thank you, sir.
Okay, thank you so much for joining. Good night to all of you. I hope this one was much helpful.
Thank you, sir.
Yeah, thank you so very much, sir.
Thank you, sir. Thank you, sir. Good night.
Good night.
Thank you, sir.